Hey, welcome to the Explainer. We think of science as being super precise, right? Clean numbers, perfect results. But what happens when the real world data is, well, a little messy? Today, we're going to dig into how scientists find the truth inside all that noise, and it all starts with a number that just didn't quite add up. So let's just jump right in with a question that seems simple, but it's really not. Is 2.84 close enough to 3? It might look like a simple rounding error, but the answer to that question gets to the very heart of how scientists decide if their big ideas are right, even when reality doesn't cooperate perfectly. Okay, so our story actually kicks off with Gregor Mendel, the father of modern genetics, and his famous experiments with pea plants. He had this absolutely revolutionary theory about how traits get passed down, but when he sat down and actually looked at his results, the numbers weren't quite the clean, perfect picture he was hoping for. And here, you can really see that gap between the theory and what actually happened. Based on his hypothesis, Mendel predicted a super clean 3-to-1 ratio of tall plants to dwarf plants. But after counting more than 1,000 of them, what he actually got was a ratio of 2.84 to 1. So, was his whole theory wrong? Or was this just, the unavoidable messiness of doing science in the real world?
And that right there is the huge challenge, isn't it? Our world is just full of random chance. I mean, if you flip a coin 100 times, you'd be really surprised if you got exactly 50 heads and 50 tails. So how does a scientist know when their data is close enough to support their big idea versus when it's time to admit defeat and go back to the drawing board?
To answer that, we've got to get a handle on the basic rules of the game. And that game is probability. Before scientists can even test an idea, they use these rules to make a solid prediction about what should happen if they're right. Let's look at the two big ones. All right, first up, we've got something called mutually exclusive events. This is basically the either-or rule. All it means is that if one thing happens, something else can't happen at the exact same time.
Just think about rolling a die, right? You can get a 4, or you can get a 6, but you can't get both on the same roll. They're mutually exclusive. So to find the odds of either one happening, you just add their probabilities together. Simple.
Okay, the second big rule is for what we call independent events. This one is the and rule. It's for when the outcome of one thing has absolutely no effect on what happens next. Let's go back to that die. Say you want to roll a 4 and then roll a 6. Those two rolls are totally independent. Getting a 4 the first time doesn't change your odds of getting a 6 on the second. So in this case, you multiply the probabilities. Okay, and this is where things get really cool. These simple rules, the either-or and the and rules, they're not just for board games. They are the fundamental building blocks scientists use to create hypotheses that you can actually go out and test. Yeah, Mendel didn't just pull that 3-to-1 number out of thin air. It wasn't a guess. He used these very rules of chance, combined with his theory about dominant and recessive genes, to mathematically predict that a 3-to-1 ratio was the most probable outcome. His hypothesis was built on a foundation of math. All right, so we've got Mendel's prediction on one side and his kind of messy real-world data on the other. To figure out if they actually match up, we need a special tool from the statistician's toolkit. It's called a goodness of fit test. And this is where our hero comes in, the chi-square test. Its whole job is to boil everything down to a single number that measures the gap between what you saw, your observed results, and what you expected to see. Basically, it puts a number on the messiness. The best way to think about it is like a recipe, really. It's just 4 simple steps. You figure out what you expected, you measure how far off your actual results were, you do a little bit of math, and then you add it all up. And what you're left with is one single, incredibly important number, your chi-square value. So let's actually plug in Mendel's numbers and see what happens. You can see there's a small deviation for the tall plants and a bit of a bigger one for the dwarf plants. When we do the math and add those two values together, we get a total chi-square value of 0.60. So we have it. Our number is 0.60. But what does that even mean? Is that a big, scary number that means we're way off? Or is it a small, happy number that means we're okay? Well, it is time to deliver the final verdict on Mendel's big idea. It really all boils down to this one simple comparison, like a final showdown. We take our calculated chi-square value, our 0.60, and we put it up against something called a critical value. Think of the critical value as a line in the sand. If our number is smaller, then the messiness is probably just random chance. But if it's larger, then something more significant might be going on, and we might have to reject our hypothesis.
So what is this cutoff? Well, in science, it's called the level of significance, and the standard convention is to set it at 5%, or 0.05. What this means is that scientists are basically agreeing to take a 1 in 20 risk of being wrong and throwing out a perfectly good hypothesis. It's a calculated risk they take to avoid getting fooled by pure random luck.
Okay, so for this experiment, what's our magic number? What's that critical value? Well, for an experiment that has two possible outcomes, like Mendel's tall or dwarf plants, which statisticians call 1 degree of freedom, the critical value at that standard 5% level is 3.841. That's our line in the sand. Any chi-square value we calculate that's below that number is considered an acceptable fit.
And remember, the number we got from Mendel's actual messy data? It was just 0.60.
And here it is, the moment of truth. Our number, 0.60, is way, way smaller than that critical cutoff of 3.841. The difference between what Mendel actually saw and what he predicted is, officially, not statistically significant. It was just noise. Mendel's hypothesis stands. You know, it's funny. In the world of stats, you never really prove a hypothesis is true. The language is much more cautious. You say you fail to reject the null hypothesis, which is a fancy way of saying that the data seems to support your original idea. So yes, after all that, Mendel's 2.84 was, in fact, close enough.
And that's really the whole point here. This is how science works. These statistical tests, like the chi-square, give us an objective, mathematical way to make a judgment call. They allow us to build real, confident knowledge, not from some perfect, idealized world, but from the messy, chaotic, real world all around us.
And you have to remember, this whole process isn't just for pea plants from the 1800s. This exact same logic of finding a clear signal inside of noisy data is at the absolute core of modern science. It's how we test if a new drug actually works, how we discover planets orbiting distant stars, how we find new subatomic particles. Which really makes you wonder, doesn't it? What other incredible discoveries are out there right now, just hiding in some messy data, waiting for the right tool to pull them out?